Hi Year 12 Maths General students. This is another topic test on geometric sequences as part of the Unit 3 content from the Queensland General Maths syllabus. And again, similar to other topic tests, I've written these questions based on the sample assessment questions that QCAA have released, just as extra practice for students. You'll see that in total there are 11 questions, simple familiar questions, complex familiar and complex unfamiliar questions. So feel free to pause the video and attempt the questions at any stage. As in previous videos, you'll find a copy of the questions as a Word document in the description to this video that you can download and modify, practice, however you want to use it. Okay, so we'll talk through each of the questions and invite you to press pause, attempt the question yourself, and then work through the solutions. Starting with question 1 is a simple familiar. It's asking you to identify the recursive rule for the geometric sequence 8, 24, 72, 216. So remember, with the recursive rule, you're trying to find the common ratio between each of the consecutive terms and build it from that. So have a go at the question and we'll check in shortly. Hopefully you identified when looking at the sequence the first term is 8, and using any pairings of consecutive terms, you found that the common ratio, or R, was 3. That gives you the recursive rule of Tn plus 1 equals 3 times Tn, given that you've recalled the recursive rule pattern correctly. Moving on to the second simple familiar question. Here we're given a recursive formula where our first term is 4 and the recursion itself, Tn plus 1, is 5 times Tn. So you should be able to identify there that 5 is your common ratio. Your job is to generate the next 3 terms in the sequence. Again, we're going to look at graphically displaying the first 5 terms of the sequence on the grid below, and then have a look at the shape of the graph and state what type of model best describes the trend of the graph, choosing from the following descriptions. So you've got to choose from a linear growth, exponential decay, linear decay, or exponential growth. Okay, have a go at the question by pressing pause and check in shortly. Hopefully you successfully used the recursion formula. So given that your first term is 4, we want the next 3 terms, so we want the second term in the sequence, so we're just multiplying our first term by the R value to get 20 as our second term, third term is 100, fourth term is 500. So if I continue that and create this table of values to get B started, we should have those values generated to give you 5 sets of coordinates to plot, remembering that your positional value goes on the bottom, so your n value, and the term value itself goes on the y-axis. And to answer question C, you should be able to see that it's exponential growth. Moving on to question 3. This simple familiar question is asking you to determine the 6th term in the geometric sequence 3000, negative 600, 120, negative 24. So think about what you need to do to find the 6th term. You definitely need to generate some sort of rule to help you get to the 6th term, or perhaps you'd prefer to use recursion. And think about what values you need to identify. So what's your first initial value, T1, and what's your common ratio, or R value? All right, give it a crack and we'll see how your solution compares shortly. So the first thing I would have written down is that the first term is 3000. And then following that, I want to calculate my common ratio R. So no matter which combination of consecutive terms, you should end up with a common ratio of -0.2. Using the formula sheet rule for a geometric sequence, subbing those values in, your rule should be 3000 times -0.2 to the power of n minus 1. Now, it's super important, remember you cannot combine the 3000 times -0.2 to the power of n minus 1. Okay, I see that mistake all the time, and you just can't do it. From there, to find the sixth term, you're simply using the rule you've created. Our sixth term, substituting in n is 6, means that we end up with -0.96 as our sixth term in that geometric sequence. Moving on to question 4, we've got a graph here showing us it looks like a geometric decay, and you have to identify the first term and recurrence relation that matches the graph below. So think carefully about how you could find that information from the graph itself and give the question a go. Okay, so reading from the graph, you can see that this first point is quite easy to identify. When n is 1, Tn is 100. So that gives us our first term and its value. The second term, if you read off the graph, is 50 if you do a bit of interpolation. So if you simply use that, you should be able to find that the R or common ratio value is 0.5. So our recurrence relation is Tn plus 1 equals Tn times 0.5. Okay, question 5 is a simple familiar question where we're looking at a population of crows around the Redlands increasing by 2% every year. So it looks like some sort of exponential growth happening here. There are currently estimated to be 3,400 crows in the Redlands. So they've given us the original number of crows at time 0, okay? So this question looks like we're going to be using our exponential growth formula, which remember is just an application of geometric sequences. Firstly, you have to write down the rule for the number of crows after n years. Figure out how many crows there are after 4 years, so you're going to use that rule, and then work out how many years it will take to double the current population. So you're going to solve for n there. Alright, so have a good think about how you could come up with a formula to describe this scenario or to model this scenario, and then go from there. So press pause and give it a crack. We'll check in very shortly. Alright, given our exponential growth model, remember it's that slightly varied formula to the geometric sequence rule, where we talk in terms of an initial value and we're talking about time after our initial period. So given our exponential growth model, that means our initial value, or A0, is 3,400. Our R value is, because we're doing 100% plus 2% every year, that means we're growing by 1.02. So if I simply substitute in my known initial and my known rate of growth, that means my rule to describe the growth of crows every year is going to be Cn equals 3,400 times 1.02 to the power of n. And remember, you cannot combine the 3,400 and 1.02. You have to leave the rule like that. That's as simple as you can get. For part B, we then just use the rule by substituting in n equals 4 for 4 years, and you should end up with a population of 3,681 crows. because remember, you cannot have part of a crow. So you have to round that value up to the nearest whole crow. Lastly, we have to find out how many years it will take the current population of crows to double. So what is double the population? That's 6,800. And there's two methods that you can use to find n here. The first method for most Maths General students is just simply using trial and error of n values. So what value of n will end up giving us 6,800? So if I logically pick a value that's a bit higher up, so let's say after 30 years, I get a population of 6,158.63. So that's a bit too low. I then check 10 years later and the population's too high there. So kind of narrowing down my n value, I tried 35 years, not quite 6,800. 36 years, I have exceeded double. So that means sometime within the 35th year, I'll get to that population of 6,800. So with my Maths General students, I have taught you how to use logs, and particularly for other students that may have come from math methods, you will know how to solve for n in an exponential function or a geometric sequence. This is a more precise method where we're simply using logs to effectively pull down that indice. And when you solve for n, you end up with 35.003 years. So that's agreeing with our trial and error method. In the 35th year, after our initial value, the number of crows will double. It's definitely not expected that Math General students know how to use logs, but it's a very handy skill, quick to do, and precise. All right, question 6 is an opposite scenario to question 5. So instead of looking at a growth question, we're going to look at exponential decay. And this is looking at a laptop that was purchased new for $2,950, and it's depreciated using a reducing balance depreciation method with an annual depreciation rate of 4.2%. Our job is to determine the rule for the value of the laptop after n years. Again, you're going to use that exponential model, but your R value will simply be less than 1 this time because we're looking at a decay model. We'll then use that model to find the value of the laptop after 6 years in B. For part C, we're going to look at how much the laptop depreciated between the second and third year. Okay, so have a think about how you can approach that problem. Press pause, give it a go, and check in after you've had an attempt. Okay, so our initial value is 2,950, which is also our A0. Our R value is just simply minusing that 4.2% from 100%. This is just another way you can show how to do that. So you should end up with an R value of 0.958. That gives us our rule when we substitute it into our exponential model of A equals 2,950 times 0.958 to the power of n. You have to then in B use this by substituting in n is 6, and when you evaluate that, you should have a value of the laptop after 6 years of $2,280.42. Lastly, for part C, you're simply finding the difference between the value of the laptop after the second and third year. Finding the difference, you should find it's depreciated by $113.71 during that second year. Moving on to our complex familiar type questions. Question 7 we're looking at an investment of $5,000 made at an interest rate of 6.8% per annum. We have to determine the number of years it will take to grow to exceed $12,000. Looking at this question, even though it doesn't say it, I would assume this investment is growing with compound interest. So we would use an application of geometric sequences where we'd use the compound interest formula, which you'll find on your formula sheet. So see if you can have a go at doing question 7, and we'll see how you went. Checking in here. From your compound interest formula on your formula sheet, we know that our principal amount is $5,000. Our R value is this 1 plus I in brackets here. So if I take the 6.8%, I should have that R value of 1.068. That gives me a compound interest rule to use for this scenario. So the account balance, or A, will be 5,000 times 1.068 to the power of n. And you need to therefore find or solve for n if our balance is going to be $12,000. So many of you will use the trial and error of n values to find this. So using a bit of educated guesswork, I started at an n value of 10, and I found that that gave me a balance of $9,653.45, which is way too low. So then I jumped up to 20, which gave me a balance that was too high. I then dropped back down to n is 15 years. Again, that gave me a balance that was a little bit too high, which means I was close. So then I dropped it to 13 years. Nearly there, but just a bit too low. Once I refined that to 14 years, I found that we had exceeded the $12,000 we're after. So I concluded that sometime in the 13th year, it will exceed $12,000. Some of you would have preferred to use logs. So again, just substituting the 12,000 in as your A value and solving equations where you'd isolate your n value by taking the log of both sides. Therefore, you'd find that n is 13.31 years. So again, confirming that after the 13th year investment, you would exceed that $12,000. Moving on to question 8, a complex familiar question. We have another financial situation here. We've got a loan of $6,800 charged at 3.2% compound interest every year for 10 years. How much interest was charged during the 8th year of the loan? So here again, think about using your compound interest formula. So have a think about how you could work out the amount of interest that was charged during the 8th year of the loan. So remember that will be between the 8th year balance and the 9th year balance. Give it a crack and we'll see how you went. Remembering that your compound interest formula is on your formula sheet, we can write down that our principal was 6,800. Our rate that goes in that brackets there is 1.032. Therefore, your rule to find the account balance is going to be 6,800 times 1.032 to the power of n. Remembering again, you cannot combine those values there. Common mistake, don't do it. From here, we need our balance after the 8th year and after the 9th year, because we need to work out how much interest was charged during the 8th year of that loan. So if n's 8, substitute in and evaluate, and I get a balance of $8,748.76. After the 9th year, a balance of $9,028.72. So if I look at the difference between those two values, That means that the interest that was charged on that loan during the 8th year was $279.24. Question 9 is the last of our complex familiar questions. The question says single-use plastic usage has been reducing by 18% every year since 2017, where an estimated 150,000 bags were used in Brisbane. Model the situation and predict in which year plastic bag usage will be estimated to be below 50,000 bags. Okay, so this seems like a decay, exponential decay type question. So think about how you could develop some sort of rule to model what we're seeing in this scenario. And then the objective of this question is to find the amount of time that's gone by. So you're going to have to solve for n here again. Okay, so give it your best shot and we'll check in to see how you went. Okay, how did you feel with that question? Hopefully you used the exponential model to come up with a rule. So our initial value is 150,000, so that's our A0. Our decay rate is essentially 82% of the previous year, so our R value is 0.82. Remembering that decay is less than 1 and growth is more than 1 as your R value. So our model is AN equals 150,000 times 0.82 to the power of n. So n represents the number of years that have gone past. Alright, so let's find n when our number of plastic bags is around 50,000. So most of you will use the trial and error values of n. So I just picked 10 years as a educated guess, and I got plastic bags of 20,617. So I picked a value that was a bit too low there. So scaling that back, I went to 5 years past, and that gave me plastic bag value that was a little bit too high, but I know I'm close. So then I tried after 6 years, and that gave me a value that was a bit too low now. So that tells me that sometime during the 5th year after 2017, so in other words during 2022, the bags will reduce below 50,000. Alternatively, for those that are confident with logs, you could find a bit more of a precise solution there. So by subbing in your 50,000, isolating the n value by taking the log of both sides, then you end up with an n value of 5.6 years. So again, agreeing with our trial and error, in the year 2022, the bags will reach below 50,000. Question 10 is a complex unfamiliar. Here we have Margaret, who's an environmental biologist, watching the rise in population of white moths as the population of black moths declined in a new developed suburb of Brisbane because of the increased light in the area. Margaret estimates that the white moths population grew by 5% every year and the black moths declined by 9.5% every year. Her current estimates on the present population is 2,500 white moths and 3,200 black moths. Your job's to model this situation using recursion and estimate the number of years that will pass until the white moth population exceeds the black moths population. Alright, so we're told that we've got to use recursion here. So think about developing a geometric sequence to model the white moth and black moth populations, and go from there to see if we can find where they become exceeded. Press pause and give it a go. All right. So I used recursion to set up models for the white and the black moths. And you can see that I've just worked out the first 4 years for both the white and the black because I noticed they were becoming closer and closer to each other. And to answer the question, because this is like a trial and error recursion question, somewhere between the first and second year, the populations will become equal, and sometime between the first and second year, the white moth population will exceed the black moth population. If you're curious on exactly what point this happens, even though the question doesn't ask for it, I just used a bit of GeoGebra to plot the two models to find out exactly when that would happen. And the exact solution is after 1.66 years, so 1 year and 8 months. Now, like I said, you don't have to know how to do that, but I just wanted to show you how we would find the exact point. The last question being complex unfamiliar. The third and fifth terms of a geometric sequence are 100 and 2500 respectively. You have to calculate the sum of the 10th and 15th terms. Alright, so to approach this question, you have to think about finding out what the geometric sequence rule is. Okay, given that you know the third and fifth terms and their values. From that, think about how you could then find the value of the 10th and 15th and then the sum of those terms. So press pause and give it your best go. Okay, so knowing our geometric sequence rule, knowing that my third term is 100, I substituted in those values into my formula, and my fifth term was 2500, substituted those values into the formula, and that gives me two equations where I don't know the value of my first term or my common ratio R. So this is where I can use equivalent fractions or simultaneous equations to solve for T1 and my common ratio R. So if I set up my equivalent fractions, that means that I can now solve for my common ratio R value. So using my amazing solving equation skills, you should find an R value of 5. In order to find my first term then, I substituted into any one of those initial equations and get a first term of 4. Finally, I need to know my 10th and 15th term, so I simply will substitute in n is 10 and n is 15 into my rule that I've established. And then to find the sum of those values, I just add those two terms together, and you get a fairly large number. And that's it. Hopefully you experienced some success with completing those practice questions for geometric sequences, and you feel a bit more confident preparing for your upcoming assessment. Okay, thanks Year 12s.